So there was a bit of a disruption because of net connectivity. So we're going to go by for the continuing the lecture. So this is how we can measure the speed of sound over here. And the precaution for this experiment is that the distance between the observer and the wall should be slightly bigger than 20 meters. And also the important thing is that how we count the count in between the different claps. That is also very important. That's pretty much it. And that's the completion of the echo method. The other thing that we can go, other process by which we can also measure the speed of sound, which can work, is by a blast gun method. The blast gun method is basically is that we're going to make one single loud sound, so that sound should be traveling only in one direction. So the procedure for blast gun method is actually a bit more simpler, but it allows for multiple observer to do the observation in a single go. So this is called blast gun method. We use the term blast gun method because we're going to use a hollow bullet. A hollow bullet means basically empty shell, not hollow bullet. Hollow bullet is a different thing. We're going to use an empty shell, and we're going to fire the shell, which should make a visible and audible signal at the same time, which means that there should be some flash of light or some smoke, which should be the visible signal, and there should be some sound produced at the same time. That's the purpose of a blast gun. And this procedure works in the way that there should be a person standing in a pretty far away distance, holding a blast gun in their hand. So you draw this person and label this thing as a blast gun, and there is some visible signal. Blast gun. So this person should do this thing, and further away from this person, right over here, let's say at a distance, there should be an observer holding a stopwatch in their hand. So stopwatch. And the distance between these two persons should be measured with a measuring tape, and this distance should be slightly bigger than about, I think we propose to be about 50 meter. So this distance should be approximately we can actually 50, you can write 50 meter is okay, but the preferred distance should be double than 17.5, which means this distance should be at least more than 35 meter, so that the observer can distinguish the audio signal and the video signal, audible and the visual signal differently from the source. So mentioning that the source of the sound, the person on the left, and the observer, the person holding the stopwatch, they should be about 50 meters apart from each other. Usually pretty much fulfills the requirement of this setup. The idea for this setup is that this person should be over here, should be a regular person, not sleepy, well rested, not intoxicated, and they should keep a keen eye on the blast gun. This person is going to shoot the blast gun, and that is going to produce a visual signal. It can be a flash of light coming out of the tip of the gun, or it can be a bit of a smoke coming instantly out of the gun. And when this person sees the visual signal, the person will start the stopwatch and wait for the sound to hear. Soon after, this person will hear the sound, and then they're gonna stop the stopwatch. So basically what they're doing, they're trying to measure how much time it takes for sound to travel from here through here. The underlying principle for this experiment to work out is that light travels through atmosphere or through vacuum at a significantly higher speed compared to sound. The speed of light through atmosphere is, let's say, speed of light. So we usually represent the speed of light as c, which is a acceptable constant for a lot of physics equations. That is about 3 × 10⁸ meters per second. Whereas through air, the speed of sound is approximately 350 meters per second. So you can see that there is a huge difference, which means whenever the person holding the stopwatch is actually seeing the audio, the visual signal, the flash of the gun, it happens almost instantaneously. So the light signal travels from here to the observer almost instantaneously as the signal is made, because it takes almost no time, or you can say like very small time or insignificant amount of time for the light signal to travel the distance in between them, whereas the sound should take a certain measurable fraction of time to travel from the source all the way to the person. So this is the underlying principle between this mechanism to work, which is also experienced in for natural scenarios whenever lightning happens. So if we have a strong lightning storm going by, whenever the lightning happens in the sky, in the cloud, when the charged particles actually transfers from one cloud to another cloud, the lightning is produced at that level of the atmosphere, much high above our head. Now the light produced from that high jump of charges is reaches our eyes almost instantaneously, because the gap in between is covered within a very short amount of time because the speed of light is so high. But the audio of that crackling sound actually reaches us significantly later. So but you have to understand, at the source, when the lightning happens, both the light signal and the audio signal are actually produced at the same instant of time by the same physical phenomenon. But because we are going to observe two different waves by two different detection mechanism. One is for the light rays, which we use for eyes, and another one is for the sound waves, for which we use the ears. That's why we're going to receive two different, we're going to receive the impulse or the sensation at two different time instances. So that's the underlying principle for why this mechanism should work, that light takes almost no time to cover the distance, or light takes insignificant time to cover the distance, and sound takes a significant time to cover the distance. So it is the difference of this two time period, two time. That's basically what is recorded by the person holding the stopwatch. So we measured that, and that pretty much solves our process. And because in this case the sound is only traveling in one direction, the speed equation is not going to have that 2 over here. So v equals to d over t. We simply place the distance between the source and the observer, which should be mentioned in your answer, that you measure it by a measuring tape or by a meter rule. And then the time that the person gets should be also placed underneath, and that ratio basically gives us the speed of the sound. So one of the things that is important, that how can we have the effect of repeat and average, and how can we make this experiment more acceptable, or what are the most likely sources of error for this experiment? Once again, the most likely source of error for this experiment is the human reaction time, and there is also another factor, which is the speed of air time আমি একটু পরে আলাপ করতেছি. Human reaction time can be also a factor. So which means that we, other than of making the observation only one time, we should prefer to use an average time by multiple observations. Or so multiple observation করার জন্য যেটা করতে হবে সেটা হচ্ছে that what we need to do, the same process should be done multiple times, and the person should record multiple different time by their stopwatch if there are only 2 person available. Other than that, what we can do, if we have more than 2 person available for this experiment, and we can set up a number of people with individual stopwatches at the same line away from the person. So let's say if we have let's say 5 persons over in this same alignment at the same distance away from the source, and we take the time measurement of all of those 5 persons and make an average of all the 5 persons. Now this actually solves the problem quite a bit, but also but this is actually not so much of a good idea in terms of physics experiment, because whenever we bring about different number of people, they would all have actually in precise sense, they would all have individually different amount of reaction times. 2 persons reaction time are not usually exactly matching. So but for the sake of easily doing the experiment to blast fewer shells with the gun, we can actually do this. So if we have let's say 5 person over here, the average time it takes for the sound to go from let's say position A to position B would be that T average should be the measured time of all the 5 person, T1 plus T2 plus T3 plus T4 plus T5 divided by 5. That gives you the average time, and then we can go for ahead and apply this equation over here. That's one way to make the repeat and average. If we don't have 5 person, that's the same experiment can be done for the 2 person, let's say three times or 5 times. 5 times is actually good for this experiment. and then we can go for the average. That's one way to increase the accuracy or the acceptable correctness of the number. The other important way, which is really important for exclusively this method, is the speed of air. One of the factors which actually also affect the speed of sound through air is at the actual speed of wind. So the idea of speed of wind, I can actually give you in a much simpler way, is that let's say if we have a river, you might actually have done this kind of mechanism where the current is going toward the right at, let's say, 5 meters per second. Now, if we have a swimmer who can swim at, let's say, 20 meters per second in still water. So if we have a swimming pool, within a swimming pool, the swimmer can achieve a speed of 20 meters per second, let's say. Now, if we place that swimmer in the river where there is a current going to the right at 5 meters per second, if the swimmer swims in the direction of the swim, the total speed of this person is not going to be 20 anymore, because he himself is moving forward at 20 meters per second, where the medium in which he is moving is pushing him forward by another 5 meters per second by its own virtue. So the resultant speed of the swimmer in this case is going to be 25 meters per second, and vice versa. If the swimmer was going backwards, let's say if the swimmer was going backwards in the current, I wanted to draw with red. If the swimmer is going backwards in some other case, then this swimmer's speed is going to be 15 meters per second. So what I'm trying to show you, that if the medium has a speed of its own, the stuff that passes through that medium using that medium would also be, their speed will also be affected by the medium as well, which is a significant source of error for this experiment, because in this case we allowed the sound to only travel in one direction. So if there is a significant wind flowing in this direction, the people might not be actually getting an appropriate reading, because the speed of sound or speed of air would affect the measurement of time. So the recommended method to overcome this problem is that the observers and the source person holding the blast gun, they should switch places. They should switch places. That's the word. They should swap places or switch places and redo the experiment for further measurement of time. The idea is that if we have some error in the path that the sound in the path of the sound that happens from A to B, the amount of error that we might have had over here, maybe a smaller time, maybe a bigger time, doesn't matter. That same error would be compensated if we do this, if we do the same measurement for the sound to travel from B to A. So whatever the error that might be involved in this observation will be naturally compensated for the reverse way of reverse direction for the sound transfer. So this is all a very important precaution for this method, that the observers and the source of the sound or the blast gun holder, they should swap places and redo the experiment and remeasure their time and use that time to find out the actual average to overcome any effect of the speed of air or speed of sound or speed of wind affecting the measurement of this experiment. এই পার্টটা বুঝা গেছে সোয়াপিং এর এফেক্টটা কিভাবে কাজ করে?
জি স্যার।
Any questions so far?
No.
Acha. The next topic that we have within our hand is the properties of sound. Properties of sound is actually pretty simple. There are 3 properties of sound. I'm going to talk about this. The first one is pitch. The second one is loudness. The third one is called quality or timbre. This timbre is TIMBRE, red timbre. It's not TIMBER, because that timber means wood, like from the trees. So be careful about the spelling, it's important. Pitch is perfectly synonymous to frequency, like they pretty much mean the same thing. High frequency sound means high pitch sound, low frequency sound means low pitch sound. It is absolutely or exclusively controlled by the source. If the source is making its vibration at a much higher rate, we have a higher pitch sound, and vice versa. Loudness is perfectly related to the amplitude of a certain source. So loudness is related to amplitude, and it is also dependent on the source as well. So if our source makes a larger amplitude, then we're gonna have a much louder sound produced for the same frequency. This is essentially why whenever we're trying to transmit over or transmit the sound for a large folk of people, maybe within a concert, or whenever we're trying to make a public announcement, we prefer to use large speakers where the cone that vibrates back and forth are pretty big. The entire purpose of this thing is just so that we can vibrate a big number of particles by having a large source and by vibrating them at a much higher amplitude, so that the sound can travel much farther away. So that's the importance for the loudness. So a higher amplitude of a sound, higher amplitude of a sound, or higher amplitude of a sound practically means that the particles which are being disturbed by the sound are having a much bigger amplitude. That would result in a much bigger loudness, and vice versa. As for the quality of timbre, this is actually dependent on the property of the sound, which usually is defined by this phrase. Quality of a sound depends on fundamental frequency, and other frequencies. I'll explain what this means. Quality of a sound is basically the way, the definition of quality of a sound is defined in this way. It's not actually defined by its own virtue, it's actually defined by one of its uses. The definition of quality of a sound goes like this: the property of a sound for which sound from different sources can be distinguished or recognized differently is called quality. I'll say it again. The property of a sound for which sound released from different sources can be distinguished is called quality of a sound. Now, what is important for you to pick up on this one is that if we try to make same frequency of sound for multiple different instruments, for example, in the video that we've seen yesterday, that in the concert, all the people were trying to tune up to a same frequency because so that they wouldn't sound mismatched. But we had different instruments. We had a human voice, we had a violin, we had a piano, we had a saxophone, we can have a flute, we can have a guitar, we can have a rumba, we can have a lot of individual instruments. But if we tune all of those instruments to the same frequency, it means their individual cycle or one full cycle takes the same amount of time for all the instruments. But depending upon the construction of the instrument, they all can have individually different sound. The one way to put this whole idea of fundamental frequency, I can put it in this way. Let's say we have a guitar. Now, let me just show you a guitar. I'm picking the example for a guitar because it's easy to explain. So let's say if I pick up this image, so a guitar is made up of multiple different parts. So there are 6 different strings on a typical guitar, a regular guitar, and there is a hollow box made up of wood, thin wood, and we have this fret bar, and we have these strings are actually put in tension over here by a specific value, which we can now control by rotating the knobs over here, which is called, that process is called tuning. But what I need to understand, whenever we pluck means giving a single stroke. That's the meaning of a pluck. Whenever we pluck a single stroke on a guitar string, this string starts to vibrate. If you don't hold anywhere on the fret bar, if we just pluck it normally, then the length of the string which is gonna be used for the whole vibration will be the entire length of the whole fret bar. But let's say if we put our finger on this gap, then this string would be pushed against this metal wire over here, then the effective length is going to be only this much. So a smaller length would be vibrated for that case. That's how the whole guitar can make different sounds, by changing the frequency of different position of the wire by putting our fingers in different places. Irrespective, let's say now we're plucking one string of a guitar without holding anywhere else, which means the entire length of the guitar is vibrating. Now, importantly, as if negative amplitude actually acha, I'm coming back to your question. You just একটু টাইম দাও, বলতেছি একটু দাঁড়াও। বলতেছি সবকিছু তোমার কোশ্চেন আনসার দিচ্ছি। So when this guitar string is plucked, this string starts to vibrate, and the vibration of this string is actually what the fundamental frequency of the sound is gonna be. So that's the primary frequency. There's a primary frequency for that is that is the key object which is giving us the basic vibration for the sound to exist. This sound will not be transferred to the audible ear because this vibration will affect the vibration of this wooden piece. This will cause the vibration of this wooden hollow box and the air that is contained within this hollow box. So that shape of air that will be also vibrated under the effect of this vibrating spring. And depending upon individual different guitars, for example, you can have thin material over here. You can your choice of wood, your thickness of wood, your construction material, how old this guitar has been, how much time had it been in the sun, or how much matured wood did you use. Depending upon a lot of different factors, the frequency of all of this individual material can be different. For example, if you just try to think about it, if you give a bit of a knock on the table, it's going to give you one type of sound. If you give a bit of a knock on the keyboard, it's going to give you another type of sound. So these devices, all the materials that you are surrounded by, they all have the individual different frequencies. So whenever the guitar string is going to start to vibrate, that vibration would cause everything else it is attached to it to vibrate as well, and their vibration will be merged or joined together with the original vibration and give us a complicated vibration scenario. So what I can try to show you, let's say the sole frequency of the guitar string is maybe like this. Let's say the frequency, the main frequency of the hollow box, this hollow box, let's say that looks a bit like that. Maybe the guitar fret, which is this large rod, that has a natural frequency that maybe that somewhat maybe look like this. So whenever we're going to make this sound, all of these sounds are going to get merged together, but which all of these sounds would be actually led, or they will be actually be produced by means of the fundamental frequency, which is the guitar string. So the guitar string is going to be responsible for the fundamental frequency, or the key frequency for the vibration, whereas all the other things which are involved are also going to add their own individual effect onto that sound as well. Together, the sound that we'll be having out of a guitar is not going to look, together the sound, the effect that we're going to have on this guitar is not going to look like a perfectly or pure sine curve up and down, but it's going to have a periodic variation like that. Different instruments can have different variation. That's what was seen on the last class, that if I try to show you an example, for example, something like that. If you have a look on this picture, that a tuning fork gives a perfect sine curve, whereas a flute gives us some bit of a cycle where we have a bit stuffs on the top, but we don't have something on the bottom. A human voice can look something like this. A violin can give us a variation like this. Now, important part, which image is bigger? This image is bigger. Okay, let's pick it up. I'll copy this image. So how can we actually distinguish one full cycle of a certain figure that looks such complicated? How do we operate this? It's pretty simple. To observe a one full cycle, we simply have to find out similar points on the similar looking points on the on the waveform, or on the shape of the wave, which basically, in other words, is that we have to find out same phase particles consecutive to each other. For example, to find out one full oscillation for a tuning fork, if you go for crest to crest, let's say this much time it takes, this would be the time period. If you go for a flute, you can choose multiple similar points. For example, I can measure the flute's time period starting from this first nick of peak from this part. This much can give you the time period, or you can choose to measure the time period from this crest to this one. So if what I'm trying to do is that I'm trying to choose similar points on the shape of the wave to define how much is one cycle. If you go for a voice, if you have a look over here, and for the case of a voice, we have this part down and then up and then down a little bit, then we have a little bit of smaller amplitude going by, and then the large amplitude goes on. So which means if I try to show you, I mean, from this part to this part can be considered as one time period, or from this part through this time can be considered as one time period, or if you want, you can also define, let's say, from this point of time through this point of time, the smaller crest, this much can be also considered to be one time period. So defining one time period basically means to find out the time it takes for the wave to complete one full cycle, which in a visual form of a sound wave can be observed for any 2 points which are identical and repetitive. So that's how we can do this. For a guitar, it's going to be pretty much same. If you just have a look at this shape, there are so many repetition, but you should be seeing that if you start observing from here, the next time period would be over here, and the next one would be here, the next one would be here. Or if you want to go for the smaller peak crest over here, we can say this much and maybe this much and then maybe this much. So observing the time period can actually make it say. Acha, one of your students actually asked me a question that why is there a break after each segment in the flute, and why is it not continuous like the other parts? One of the reasons that flute has a break, as far as I know, is that flute only makes sound as long as we blow into the flute. So it actually does not have a continuously vibrating mechanism like a guitar or like a tuning fork. I mean, the way the tuning fork works is that we give it a vibration, and I mean, let's say I'm gonna hit the tines, which is the two ends of the tuning fork, with a rubber hammer or maybe on my hand, and I don't have to feed any more energy within the system. That initially given energy is going to cause the vibration to keep on, and eventually we can have the tuning fork work just like that. Whereas for the flute, the sound is going to only continue as long as we keep blowing into the flute. So every individual holes which is kept open actually add a certain bit of variation over here. So this is the reason, and there is a large hole at the end which particularly dissipates all the sound energy through the flute. That is the reason that it requires a continuous input of energy for the sound to continuously go on. That's why we have a vibration pattern like that. This is discontinuous. It means if you give a single blow, you're going to get a sound like that. বুঝাচ্ছে?
জি স্যার, কিন্তু তাহলে ভয়েসের ডায়াগ্রামটার মধ্যে ব্রেক নেই কেন স্যার?
আচ্ছা, ভয়েসের ডায়াগ্রামে ব্রেক না থাকার কারণ হচ্ছে the way our voice works is also by the vibration of our vocal cords, which are very small, not very small. I mean, they are very thin string kind of attachment which are placed within the Adam's apple. That vocal cords are vibrated by the effect of muscle, and how longer should that muscle vibrate is controlled by how longer should the vocal cord should vibrate is controlled by the muscle. So for example, if I'm trying to make a sound continuous sound like I have a continuous vibration like that. If I'm talking in a different manner, by changing the shape of my mouth, which is basically the other frequencies, I'm actually making different sounds. So for example, I have a fixed shape of my buccal cavity, the inside of my mouth. I have a fixed shape of my of my tongue and the gums and the teeth and whatnot. So my vocal cord vibration added up with all the variation added from all of this environment together makes my voice, which is unique compared to anyone else. But the vibration of the voice can be also fed from the muscle, which can be a continuous process. So we can choose how long the sound should go by. So, but within the flute, to produce the sound, we have to continuously give in the input for each individual sound. That's why it has a bit of a break. That's so far I know, but I'm not completely sure about this. I'm going to have a look over here. Why do we have a break sign over here? I'm going to have a look for this and get back to you. But that's what I believe is correct from my earlier experience as far as my memory helps me. But I'm going to have a look into it once again. Quality part ta ki bujha geche bolapan?
জি স্যার।
Did you understand this defining phrase that I wrote, that quality of a sound is dependent upon the fundamental frequency and other frequencies. These other frequencies are fed from the relevant other equipment which surrounds the original main source of sound. Together they produce a combined effect. আচ্ছা, এখানে আমার কাছে চ্যাটে দুটো কোশ্চেন করছো তোমরা। ইরফান একটা কোশ্চেন করছো হচ্ছে what does it mean, what does negative amplitude mean? Negative amplitude is not supposed to be a very commonly used term, but what I understand from this term by just looking at the term is that whenever a particle vibrates, for example, if I try to draw the displacement versus time of an oscillating particle, let's say the displacement versus time of an oscillating particle is like that. So we can say that this is the positive amplitude plus a, and at the lowest part we can have the negative amplitude minus a. Considering that this is a displacement, which means this is a vector quantity, because the way we define the amplitude is that maximum displacement of an oscillating particle from its equilibrium position is defined as the amplitude. So if we consider in the upward direction, which is considered usually the positive direction, we can have a positive displacement, positive amplitude over here. We can have a negative amplitude over here. So that might mean as the negative amplitude for the case of an applicable graph.
No, sir. I'm trying to say what would a negative amplitude sound like?
Negative amplitude itself by itself cannot exist. If you want to have sound, you're going to have positive amplitude and negative amplitude both, because for one whole cycle to fill up, you need to have the particle moving up and down both. You cannot have a particle only moving down and give you a sound. That is not going to happen. You need to have the particle move back and forth above the equilibrium position. This is obvious. So exclusive the negative amplitude, I think it's not possible to produce in a regular case. As far as I know, negative amplitude itself by itself cannot exist, because the particle should have equal amount of movement on both sides. Because
Sir, could you repeat again? You're cutting off.
As far as I understand, the negative amplitude by its own cannot exist for any such example, because the particle has to move up and down on both sides of its equilibrium position for the sound to exist in the first place. So exclusively negative amplitude shouldn't sound like anything, because that is not supposed to happen. Particles should have positive amplitude and negative amplitude both, just to make sense of one full cycle, and one full cycle gives you one pulse of sound. Multiple cycles one after another gives us a continuous sound. I mean, one small way to just put in answer. So Frank, coming to power call what they say. One small way to put down this answer is that negative amplitude on its own is not possible, because a sound should be created by the vibration on both sides of the equilibrium point for the oscillating particle. So any full cycle should have positive amplitude and negative amplitude both included within its cycle. That's my response.
Okay, sir.
Bucho.
Yes, sir.
Shoptoshi je question korchila, as the length increases, does the amplitude is increasing? No, as the length increases, the frequency of the sound decreases, because a longer length of an object or a bigger object tends to have a lower natural frequency because of inertia. I mean, if you have a more massive object, it tends to move slowly. So the length of the string actually controls how would be the frequency of that string. However, the amplitude of the string is dependent upon how strongly are you stroking the guitar strings. If you stroke it strongly, like really putting in your nails, then it's going to make a loud sound. That's going to cause the particles to vibrate more. So how much amplitude you give depends upon how much of a initial displacement are you providing to these strings. So I mean, playing with strong force or vigorously will increase the amplitude of the sound, whereas changing the length of the string is going to change the frequency of the sound. Together, it can produce a huge variation of sounds, basically what makes the equipment a musical instrument. বুঝছো কি বলছি?
জি স্যার, বুঝেছি।
আজকে একটু থাক, আমি গ্রাফের কোশ্চেনগুলো ইনশাআল্লাহ নেক্সট ক্লাসে তুলবো, এবং হচ্ছে তোমাদের ওয়ার্কশিটে কিছু প্রবলেম আছে, ওই গ্রাফের জন্য ওয়ার্কশিটেরও হেল্প লাগবে, এগুলো আমরা ইনশাআল্লাহ নেক্সট ক্লাসে দেব। নেক্সট ক্লাস কবে? ফ্রাইডে। সো আই উইল সি ইউ অল অন ফ্রাইডে ইনশাআল্লাহ। আর হচ্ছে আমি আজকের লেকচার এবং গত ক্লাসের লেকচার একটু পরে আপলোড করে দিচ্ছি, so that if any of you need to see it again, you can take help from there. Thank you very much. Assalamu alaikum.